Okay, yeah, so essentially what we're going to be talking about today is everything that happens to data from the very beginning of an evolution of transformations to the point that it reaches the model. And I want to kind of contextualize this presentation within this concept of data-centric AI, which is the idea that we can improve results on statistical modeling tasks, not by iterating on the model, but instead by iterating on the data. Now, a lot of these talks discuss ways to filter data better, collect more appropriate data, and these are all important scientific questions, but they're not the focus of this talk. What we're going to be discussing is the engineering around the evolution of data as it moves from that source of data to the model during the training itself. And we're going to start by defining what data loading actually is. Now, I'm sure folks are familiar with the data loader abstraction, but I'm kind of speaking more philosophically here. And what we're really doing is we're starting with this known material world of physical forms that we all recognize, and we're transforming it into this more confusing, unknown vector space, simply because that's what our model is expecting. Now, to be clear, this modeling part and any implementation of the model we're not going to be discussing. So we're strictly focusing on solving this problem very narrowly. And so now that I've kind of given the high-level formulation of what we're trying to do, we're going to discuss about why we need abstractions to progress through this evolution of data, which abstractions to use, and then for each of these abstractions, meaning, compilation, and execution, we're going to discuss them in a bit more detail in terms of what they accomplish in terms of functionality and how they help us work within the data in all the steps and evolution that it goes through before it gets to the model. So working backwards from first principles, we need to think about what the value of data is to us as people working with statistical modeling. So the first kind of data value is the source semantic information. So this is the idea that if I have objects that I see in the real world, I can identify what they are, I can understand certain measured quantities about them, and I know where they came from, right? So these are the kind of things that I appreciate about the material world, in that I can identify and interpret what I'm seeing. But, we are trying to do some kind of modeling here. So if we want to make a pumpkin soup, we also want to have some kind of semantics about the task at hand, right? So in that case, that is a recipe, which builds on this source semantic foundation and infuses it with a sense of task-related constraints that allow us to kind of take a further step into actually modeling the problem we're trying to solve. And the last thing is, and again, this is because we're kind of situated inside of a computational system for most of our modeling tasks, we need to ensure that we have data that can be efficiently represented for integration with accelerators, heterogeneous compute. And in the pumpkin soup analogy, that would be like ensuring that your ingredients can fit in the lid of this auto dicer, right? We want to make sure things run fast to make sure that we can actually leverage the computational resources that we have. And so building on this kind of set of principles around what we want to get out of the data, I'm going to propose that through this evolution of the information that we feed into the model, we break it into three abstractions. The first one being meaning, which is really focused on having these clean source semantics. We here describe identity of objects, the relative quantitative units that are important, and the intent of the source information. So this is where we ensure that the world as we understand it corresponds to how the data was encoded in the data sets that we have. So systems that you may want to keep track of here are any storage systems that are involved, any kind of data generation pipelines, and any human interfaces that you want to use to look at the data. The second abstraction level I'll be referring to as compilation, because it takes this source semantic information, and here we infuse the source information with some kind of task-specific ideas of the problem that we want to solve by providing a strict protocol for the model to consume. And this is the layer usually where you have application level integrations. You might be concerned with a tokenizer for folks that are familiar with that. And then after you have this strictly defined semantic protocol for the task, you want to finally reformat the data without changing task semantics to ensure that it can be consumed efficiently by the model or the general statistical process that you're working with. Now, there is kind of another notion about just doing a one-pass tokenization over all your data. And my argument for this is, or against this, is that it's a little bit abstract and hard to work with. You'll be working with a lot of problems in debugging the middle of this pipeline. You'll have to spend a lot of engineering energy and effort to ensure that you have ergonomics for every single step of the way with a single or ill-defined representation. And finally, you're going to be keeping data that you might not need throughout this entire evolution. So these are the kind of things to keep in mind when you consider the need and validity of using these abstractions to represent this evolution of data as it goes from source to model. So starting with meaning, this is, like I said, the closest to the source representation. And although I'm discussing it as a ground truth, we should always keep in the back of our minds that, of course, any data, even if we keep it as raw as possible, has still been implicitly transformed by the sensor used to record it. But nevertheless, it is the most interpretable kind of data that we have, and it allows for communications between teams, right? You can show somebody an image and everybody can discuss and kind of make decisions about it communally. But keeping it only raw is insufficient. Ideally, here we create a typed contract over the data that allows us to programmatically encode our assumptions about the understanding of the world that we have, and again, ensure that what we have in our data is representing that. So validation here is very important. And if you want some ideas of how to incorporate this kind of validation into your workflow, you can get some examples here. So one is that if you're working with language, you want to make sure you maybe don't have any white space, you don't have the incorrect language, and we'll talk about that a bit later. If you were working with any kind of temporally grounded data, you want to make sure that timestamps are monotonic. You may have certain assumptions about intervals of time, whether or not they can overlap. And if you're working with geometry, let's say in robotics or any kind of kinematic data, then you want to make sure that any shapes, units of measurement of distance, and angles all kind of correspond. And as you enforce these rules, make sure to keep in mind that the sensor that's used to record this information in the world has already transformed it. And I want to say that this layer of abstraction, the semantic source abstraction, is the one that is the most important, not only because you can enforce your understanding of the world onto it, but also because you don't want to have all of this data get up until the model, spend needless computational resources transforming it just to drop it at the last second. So the very beginning of the data processing journey should start with eliminating as much data as possible. Now, in terms of implementation, this is kind of a minute detail. At Perceptron, where we build foundation models, we work with PyData because it has some nice quality of life features there. But it really doesn't matter. You can use something like data classes or adders, whatever validation library you're comfortable with, as long as it has enough flexibility to accommodate your use case. And in the language scenario, okay, that's a little bit hard to see. But essentially, if we want to make sure we don't ever train on any Chinese data when we're modeling the English language, which might be the case because China has a big AI infrastructure and commercial economy, you're going to see a lot of Chinese open source artifacts and therefore a lot of Chinese language information in open source datasets. So what you can do is you can create a type that encodes a validation rule that if you input any text into it that contains Chinese characters, it'll raise a validation error. So just to see that abstraction in action, we can see that if we input something like language turns intent into action, then that'll be fine. If we add Chinese characters, it'll, as expected, raise a validation error. And of course, if we have a mixed case, it'll still raise. So this is nice because now we're building on a solid foundation of what we believe our language data to be. But on top of that, having these typed ergonomics around this close to the source data allows us to, in fact, visualize it, which is a great form of communication between people on the team. And these visualizations in particular, all of these, were generated by hooking into the API on top of the type that I created. So this is another thing that you're investing in is interpretability. And if you want a more complex example, you can look at the hardware specifications of a robot, for example, identify the maximum acceleration that it tolerates, and use velocity and time sensor data to ensure that you're within the bounds of what is reasonable for regular robot operation. My point in providing these examples isn't to say that this is specifically what you should do. My point is that you should consider for your task what kind of understanding and domain expertise that you have about the world, and enforce those rules programmatically on your data as close to the source as possible. And this gets you, like I said, inspection, it gets you safe evolution of your data set, and it lets you quickly diagnose issues as it goes from the source to the model. Like I said, you want to catch things as early as possible. Now, you do have to do some work in migrating data. You have to stick to stricter invariance in what you assume about the data. And most importantly, you actually have to do the work of designing the data schema that you want to use to represent it. But this pays off, in engineering terms, as I've already described, but it's also a useful mental exercise, but it requires you to kind of, at a mental level, formalize your assumptions about what data you're training on. And this is the representation that you're going to be storing. So we're at a point now where we're just going to be reading the data from some kind of a file storage system. So that could also be a database, but it can be an S3 bucket, or it can be a local disk. So this is where you can also start to design containers around these typed representations. So we have essentially a custom file type that contains a header and a byte stream. In the header, we have this count that lets you identify what byte offset you want to read into. So let's say we want to look at sample 1. That's essentially a linearized, serialized representation of our typed format. So think about text input there. And by identifying these offsets that correspond to that first sample, we have the ability to, with high granularity, pick out only the data that we want. Now, this might seem somewhat orthogonal to the question of having these abstractions over our raw source data, but the important thing is what we do next, which is that first we decompress, because there's some nice things there about overlapping your CPU computation with your networking. But the important thing is that at this point, you should validate the data again. And the reason is that you want to confirm that the rules that are encoded in your code base as it is today is the same or corresponds to the rules that were enforced at the time that the data set was created. And we're at a point now where if we've read this data from storage, we've validated it, we're operating on solid ground in terms of what the data fundamentally is in terms of its identity. But you'll notice there's still many ways that we can represent text data. We might want to transform it, and we certainly don't have any strict protocol or sequence to do our statistical modeling on. And this is where the compilation phase or compilation layer abstraction comes in, where we essentially implement a strict order or protocol for the data to be modeled, suitable to our modeling task. Now, this is obviously very important for language modeling. Because of the next token prediction loss supervision, we might imagine something like a user query, right, as input. The model does some thinking, and you get an answer. And that's what we expect, and that's perfectly valid. It's invalid, of course, to start with thinking, then move to the answer, and then finally represent the user query. Now, these are kind of simple examples, but it's all to demonstrate that the sequence of information as it is presented, or more generally, the format of your data, is intrinsically tied to your modeling approach. Now, there are probably some exceptions, so I do want to take a moment for folks to think about how exactly this interacts with your modeling problem and whether or not this is even the case. But to kind of broaden this example, in the context of VLM, you might start with an image, and then after that, on the tail end, get a text response. Vice versa if you're working with image generation. So these are further examples where the sheer organization of data literally defines the modeling task. And internally at Perceptron, we work with the mHarmony abstraction for this compilation, where what we want to do is turn that intent that we have around our task and encode it into tokens that we'll eventually get into the details on how we execute against those in the model. But this is what's happening during training. So we're taking a step forward in our evolution of data during training to encode this information. And how does this work? Well, in practice, at least internally, we kind of have this source representation of data. You can think of this as the equivalent to our text input type, but because we're working with multiple modalities, we get kind of a richer structured object. Now, the traditional way to protocolize this is to turn this into tokens via tokenization. But the problem with tokens that I've come to realize in working with higher level abstractions is they're really this kind of black box, almost an adversarial representation of data, from which it is very hard to reconstruct semantics because you need to work backwards from token level syntax. Okay, so if you want to find out about, where did this token come from in our source representation? What does this token mean? Who sent it? And is there any metadata associated with it? Again, this is something that is feasible, but you're going to have to implement a lot of ad hoc logic to actually trace all of the token syntax back to the tokenization rules and get that information out. So what you really want to do is you want to create containers over your token level representation that, again, represent the task that you're trying to solve. So in my particular case, if we're working with generating a foundational language model, the task that we're trying to simulate is that of an interpersonal interaction. So with that being said, naturally, the emerging representation over tokens becomes an interaction, which is formalized as just a sequence of messages. Now, all of these messages have tokens still that describe role, channel, recipient, type. In this case, role is just who's sending the message, and channel is going to be reserved for what we do with that data. And if you're wondering about kind of that low-level content of the representation of the source objects that we were working with before, we still have that in the content of the messages. And not only that, but every single token is grouped by its type and handled accordingly in the backend. So if you need access to those low-level details, you still have them, but by default, you can work with an abstraction that is ergonomic and humanly understandable. So to give an example of how this works in practical terms, you essentially just have data classes, and I know that this is likely not visible, but we're essentially just giving a code representation of what's visible here. So we just have the types, definitions, with the fields that correspond to channel, a sequence of messages, and so on. And so what would take so many lines of code to kind of initialize or create in the token space becomes just a few lines of code that has a semantic understanding and can be easily put together by a human, whether you're putting in text that gets validated, whether you're putting in images, or you need a tool call to be executed on a computational backend. That's all accessible to you from a kind of bird's eye view that makes sense to you as a human being, but that is also useful to integrate with other applications. Taking a step outside of our training process and pipeline, in this commercialized context that we perform statistical modeling in, there's a good chance that any task or problem that we solve here, we're going to need to deploy and apply to the real world. So I'll give an example of that. I'm sure most of us are familiar with the ChatGPT interface, where if you ask a question like disproving Fermat's last theorem, you're going to see some blinking as it quote unquote thinks, and then when it has a final response, you'll get clearly visible text. So how is that done? Well, you can actually, with this abstraction, start with your black box tokens that you don't know what they are and you never have to think about, because you have a semantic abstraction that can be easily parsed over and rebuilt from the token level. And then at that point, it just becomes a question of checking the channel, right? That representation that we had on every single message, and doing with it as you will. So if you have internal reasoning, you might want to hide it from the user. If you have any tools, you need to execute them. And of course, the final response just gets kind of shown to the user through a straightforward UI. And again, at a code level, we just literally do a for loop and a match statement on the type. Now, by contrast, imagine implementing this at the token level, right? It is just insane. And if you want an example of how this might work and how I know that this is how ChatGPT is working, you can look at the Harmony library from OpenAI that seeks to solve this exact problem. Or if you want to wait a little bit, we are currently working on open sourcing our multimodal harmony compilation, which I've kind of discussed in some detail, which allows for greater flexibility, agnosticism towards the types of data that you're working with, and in fact, some performance benefits as well. So keep an eye out for that. And kind of in summation, we've generated this protocol. We got out of it also this abstraction, ergonomics. We have reuse for when we want to apply our solution to our statistical modeling problem in the real world. And we also have determinism, right? By having this level of abstraction, we can comfortably use any RNG-based transformations with a static seed. So if you have any seed that you use for modeling, you do not want to be implementing that here. But for any transformations that are developing the protocol that you're using, this is the place to do so. Naturally, kind of similar to the previous level of abstraction, if you use this, you do need to do a bit more platform work. So you need to maintain this abstraction. And you are stuck in a more strict contract. So if you kind of want to change your entire model protocol, you definitely have the capability to do that, but you need to move a bit more weight around. And at this point, we started with our source semantic information, and from that, we've created a strict, linearized, again, in the context of language modeling, linearized representation that specifically is infused with the information about the task that we want to solve, right? So in this case, it was mimicking a interpersonal interaction, but whatever it may be. And this is something where we've already crystallized the task semantics of our modeling problem. And we're moving into this final layer of abstraction where we don't want to change the meaning of what we're doing, but we may have to reorganize our data to ensure that it's properly operating kind of as it is situated in a computational context. So at a high level, what does that mean? Well, it means kind of integration with the accelerator. It means that we can easily do bookkeeping for the kind of stuff that we typically do with at least deep learning. So masking certain things, keeping track of positions. And of course, most fundamentally, it still needs to carry the kind of meat and potatoes information that we need to train on. So for us at Perceptron, we use an abstraction for this called TensorStream. This is our execution abstraction. And this is already open source with a blog post on it. So definitely encourage you to check it out if you have any further kind of inquiries about it or you want to dig into it at a deeper level. But to kind of give an overview, we essentially have an event-based system where every single event carries the payload. This is the core of the data that we're modeling, right? These are the core tensors. We have our type. Again, in our particular case, we are working with multimodal data, so we do store that. And we have some data additionally about time and things like the role, which you'll see how that might come into play for some quality of life operations that we want to implement later. And at this point, we have a lot of things that we can do, a lot of operations that we can implement, like pad, pack, or move samples around between hardware. But the important thing is that we do not want to, at this point, change the semanticity of our data representation with respect to our understanding of the source data, nor with respect to the task that we're trying to solve. So we can do layout optimizations, but that's fully downstream of any kind of interpretation. And one example of this is just how we move this abstraction around between devices. So if you think about the number of systems that have to do this, whether or not that's the collator, the model runtime, the data loader, it's quite a pain, honestly, to manage every tensor individually. But when everything is wrapped together, you can build functionality like this that wraps an abstraction and moves all the data efficiently. So for example, if we have all of these events, which are separate objects, we can combine their payloads, pin the corresponding memory on the host, which allows us to initiate an asynchronous transfer from the device side. And beyond that, because we've grouped all of these events into a contiguous 1D tensor, we also only have to pay the overhead for a single instruction. So this is something that's a little bit specific to CUDA devices and hardware-to-device transfer engines. But the important thing, again, is to keep in mind that the data you're working with is situated in this heterogeneous computational context. Another thing you may want to do is use the metadata that is co-located with your payload to do things like, oh, I have 5 events, 4 of them are users, One of them is the AI itself, and we've decided we only want to calculate loss on the AI's event. Right? So that becomes a very trivial thing to do when your metadata and your actual modeling payload are co-located. Another example, let's say we want to do something based on the type of data that we're working with. So if we have text, 3 vision events, and an audio event, we can filter by the type that we have in the metadata for these events and construct a mask across all these different tensors. Now, again, if you're managing many separate tensors, you're moving them across devices, you'll usually have to implement ad hoc implementations to derive these masks based on what you want. But having all of this information accessible to you within a single wrapper really makes this something trivial, extensible, and very flexible. Now, the very last thing that we do, now that we've kind of done all of our computational bookkeeping for deep learning, we've moved the data that we have on device, and it's represented as tensors, we actually want to group them by modality, in the multimodal setting, of course, in order to kind of send it to different subsystems of the model we're working with. And that starts first by simply looking at these objects, and these are objects, not tensors, so we can just iterate over them, and group them according to type. After that, we want to compact, which is similar to that hardware transfer case, just combining the relevant tensors that we're working with to make sure that things are efficient. And to be more specific about this, not only do you have to pay the overhead of transferring the data between devices every time, you need to pay the overhead of kernel launching, scheduling, and of course the model forward pass 5 times if you do this without compaction. But if you have an abstraction that allows you to reorganize the data to make things more efficient, in this case by combining the different tensors involved, then you can get that down to 3 in our example. So we've kind of traced it from this sequence of events into per encoder single tensors based on their associated metadata. And throughout this entire process, we also tracked the different position bookkeeping schemes that we want to use for different kinds of data. Now, this is very, very use case specific, but the important thing is that something as finicky and brittle as position bookkeeping can also be addressed through this approach. And so at a high level, this gets us submodel routing. It gives us the ability to do all kinds of bookkeeping. And we get hardware efficiency for all of these small, often finicky, often complex operations where we still have to manage that complexity, but it's all inside of one abstraction. Now, the cost for this is, of course, we do need to keep more metadata because we're keeping it in the object that carries the payload. Otherwise, you would just be working with a raw tensor. We do need to traverse objects, which can be a little bit computationally costly, but because of the regime we're working with a device accelerator that can kind of operate at the same time with our asynchronous transfers, it's not so expensive. And as usual, we are committed to stricter invariance here. So at this point, we've gotten to the point where the model can just consume the data. So we walked all the way through the meaning representation, where we were closest to the source. We enforced expectations that we have about the world and encoded them programmatically into our data representation. That was loaded off of the disk and compiled into a strict sequence and protocol that is infused with information we have about the task that we're trying to solve. And we finally reorganized the layout of the information such that it was aware of the fact that it exists in a computational context and leveraged that to its maximal extent. Now, you may not need to work with exactly these set of abstractions. So a few questions I would ask yourselves are, do you need this decoupling between the different phases and the different parts of the evolution of this data as it goes from wherever the data is stored to your model? If yes, you may benefit from an abstraction here. Is your format of your data and the task that you're trying to solve actually closely connected? Again, if the answer is yes, you may benefit from this additional level of abstraction or an intermediate representation. Finally, do you need provenance and understanding about all of the decisions that were made throughout this process? Now, maybe that's because you want to be able to debug, you want to collect some kind of metrics, you need to do monitoring, or you just need to communicate with external stakeholders, like let's say for commercial reasons. Again, if that's the case, you may benefit from these abstractions. But if you're thinking about these questions and all of the answers are coming back negative, then you may honestly be better off with just a one-to-one functional mapping directly from the source representation to whatever the model will accept. And that's because the high-level important things aren't these abstractions, but the principles that are at play. The first being that you always want to design for the next boundary, right? So the semantic representation fed into compilation. We had this nice abstraction to extract data. And then the compilation representation took that in with a equally ergonomic format to define a structure over token level information. And finally, this directly fed into our layout optimizations that were needed to efficiently model our task and solve it from a statistical point of view. The second is that at every single stage, we try to only retain what is needed. I mean, imagine if at the execution layer of abstraction, we were still trying to maintain information about pixel values that were highly relevant at the meaning abstraction layer, but of course have no real purpose when trying to execute against the model. And the final thing is that every single time that we narrow the data, we do need to come to some kind of new abstraction. And this abstraction can be either designed, like we've described here, or it can emerge naturally from the logical procedures implemented from your code. I think I've made a case for why having somewhat of a top-down approach is useful in understanding the evolution of data as it goes from its source to the model. But again, in either case, an abstraction will exist. So the model can receive this very well-curated and well-packaged data. And throughout the entire process, we maintain an understanding and control over what's going on. Now, if you want to look at what we've been able to build on top of these abstractions and this philosophy of thinking, you can scan this QR code and first of all, play with our demo, check out our model, stress test things. And secondly, you can see the second link to the platform page where you can use code PyCon for $10 of API credits to kind of take that integration to the next level. And finally, I've also included for your reference the TensorStream blog as well, if you have any kind of further curiosity about that. And I think that does bring me to the end of my presentation, and I'm looking forward to questions.
Okay, one question at a time. Microphone will be sent to you. Questions? Anyone?
Yes, hello. I'm here. I don't know if it's your scope of work, but from what I understand, for multimodal models, there is an enormous amount of data that you feed to train the model. I wonder how you do the processing. Is it some proprietary software, some software that you've developed for data pipelines, for feeding the data into the model, Kafka, whatever? What are you using?
So essentially, if we're talking about outside of the scope of model training, then that's kind of a whole different picture. So this is assuming we already have our data and we're just defining the source. Now, once you get to that point, there's some kind of proprietary implementation on how to efficiently get the data into the model that still adheres to the statistical constraints of modeling. But that's kind of a whole different thing. I guess I will just say to answer, there is some proprietary stuff, and we don't use any kind of high-level library because it's pretty specialized to the modeling needs at that point because of shuffling and things like that. And also the hardware operations that we're working with. But we can talk after if we want to get into the details.
Okay, questions? Any other questions? Any other questions? One? Any other questions? Two? You have a follow-up question?
Just wondering.
With microphone,
okay.
Please.
What's the amount of data that you process? I'm just wondering.
A lot of data. So I think
Dozens of terabytes, or
I would say like more more even if you want. I think here we covered the fundamental way to organize how you think about this. Now, in terms of like a low-level implementation for scalability, that's kind of like a little bit more advanced. But to answer your question, it's a lot of data. Like terabytes and terabytes and even higher orders of magnitude, if I dare say.
Thank you. Other questions? Going one, going two. Yeah, last minute question right there. The winner, fourth row.
Hi. Oh, this is not. Oh, yeah. Okay. Thank you for your amazing talk. I just wanted to ask you about the tokenizer part. If I understood correctly, do you skip the tokenizer totally, or you just have these events that encode a lot of data, and then you use your encoder to just turn them into a digital representation? And does the tokenizer come after that, or?
Okay.
Yeah, and in general, how do you train your encoders?
Okay.
Is that end to end?
This is two different questions, but
Okay.
let's start with the token level information. I'm glad you brought this up because I don't want there to be any confusion. So the main thing that I'm arguing against is doing a single pass with every time you hit a new block here, you do some kind of if statement, and then it just goes into one stream. That's the thing I'm arguing against. Now, with that being said, all of the token level information is still contained within the containers that you use. The important thing is to make a type that wraps these individual tokens so that you actually can understand what's going on and you can connect to other interfaces, right? So all of the tokenization that you have here is still happening on the back end. You need to have some kind of token information. The important thing is that if you can group them with these higher level structures, then I think the benefits are clear. Once you start working with an abstraction like this, it's very painful to have to work with raw level tokens. So that's the first thing. The second thing of training the encoders, that's kind of outside the scope of the talk. But yeah, it is end to end, and it does consume these tokens at a high level.
I have a follow-up question.
Let's see if there are no other
Yes,
questions.
yes.
Any other question? Last chance. Okay. The floor is yours. You can ask questions for next 10 minutes.
Oh, wow. Thanks again. So basically, you have a hierarchy of tokens per event, correct? It's like a dictionary of tokens,
Yeah.
and each has its own team.
Yeah.
And you just how would you compare that to multi-code book VQVAE?
Multi-codebook VQVAE is a totally different way to tokenize your data. So this is I wouldn't think about this as something from the modeling perspective. I deliberately am trying to stay away from any modeling specific details. This is purely for you as a user to organize your information so that you can do whatever you have to do on a token by token basis. This is not a new tokenization strategy or anything like that. Any way that you would tokenize this data in a direct pass, you still do the same kind of tokenization here on the back end. It's just a question of how you organize that data so you can crystallize the decisions you make about formatting it. So you can use special multi-codebook tokenization here. You can do byte level tokenization. You can do normal word level tokenization. You can represent the tokens, the actual content of the tokens, that's dependent on the back end. But the important thing is to orthogonalize your semantic representation from what's happening on the back end. Because a lot of times what happens is you just have the back end implementation, and okay, the tokens are great, they're representing the data as efficiently as possible, but you don't have any idea of how they're actually structured in that token stream. Does that make sense?
Yeah.
Okay.
No more questions? Yeah, that's good.
And how do you optimize the number of types of event that you want to keep? Or you can go hard and take in whatever you can find in your data and just say, okay, this is a type of information that I want to tokenize. But you can also minimize it for saving tokens.
Okay, so for this kind of question of, we might not want to model all of this information. To respond to that, I would say, in practice, I can just say that we don't do it at this level. That kind of goes into the model level. But if you want to, there's no reason why you couldn't say here, oh, well, this message, like I don't like it, or there's something wrong with it. You can definitely skip that. But generally speaking, you kind of want to have information from within the model to make that decision. So operating on a heuristic here, I think, is a little bit risky. But once you get to the model, then you have a little bit more understanding of how your statistical modeling process is going, and you can make those decisions kind of downstream from this.
So, you are asking about which microphone, please? We're recording it.
No, I don't have anything to say. So I think you're asking about like these abstractions, right? Like how we decide like images, like what types we have, like how many enums we should have for role and stuff like that. Like how to design a good abstraction. I think the question is that more, not just model specific, but yeah.
Okay, so we discussed the case where the question is, okay, we want to drop some of the content that we're modeling, and so that's a modeling question. Okay, fair enough. If the question is, how do we want to represent this abstraction, and what the kind of metadata should be and how to group events, this is where you really need to keep in mind the specific task that you're trying to solve, because you don't want to think about optimization or modeling or anything like that. So I would just say that the structure of this representation needs to kind of come down to your thinking about how the task is going to be solved. So at a high level, I would just say, try to keep these units atomic. Don't keep any information that you're never going to use. But otherwise, it's really use case specific on how you want to build out these separations.
Okay.
Thanks again. And how would you compare this to the philosophy of trying to getting out of the way of the model and like not do as much feature engineering as possible? I mean, at one point with deep learning, we try to move away from that, but it seems like your philosophy is moving towards that.
Okay. I think again, I need to kind of separate. I need to very clearly separate the fact that this is still the classic tokenization, any kind of back-end embedding representation that you would usually use, and any structure that we build around that is purely for our understanding. So this is not we're not taking this and turning this into some kind of custom way to represent the data that we're modeling. It's purely an abstraction that is developed around, what is this data that I'm modeling? What does it look like? What is its shape? And how I can plug that into external systems. So any kind of a way that you would take this approach and you would represent this data somehow for the model to consume at the end, you do the exact same thing. You just have additional metadata and structure built around it so that it's easy to work with, test, validate, iterate on, test against, etc.
Okay. I think. Yeah. Okay. We have a bingo here. With microphone, please. And that's the last question because we are out of the 10-minute questions sort of window.
Okay. Thank you for the talk. Just building on that previous question that was asked. So if I'm understanding it correctly, these abstractions are helping you a little bit with like interpretability, like reproducibility, like context on like what's going on in that data stream at that point in time. And it's abstractions for you to use, but not necessarily like the model is seeing this abstraction that you have here, just the token stream. And can you give like a toy example? Just like, let's say it's an image of a hot air balloon or something.
Yeah,
like,
so this image
what does it look like?
So first of all, just to reaffirm what you said, that's absolutely correct that I'm talking purely from a human engineering standpoint. We are in the software engineering stream, so I'm not giving any recommendations on solving kind of a modeling issue. So this is not going to resolve your modeling problems. This is just going to ensure that you can work with the kind of pipeline that you've already established in a more convenient and kind of professional way. Now, in terms of working with let's say starting with this hot air balloon, this process of building out this interaction with these messages, naturally you start by, let's say the image is the first thing that comes up. So then that'll be a given message. And then that message inside of it will have the associated metadata that you might have with it. So if you want to keep track of who is meant to be sending this message or what you intend to do with that kind of information, then you would have that metadata. So in the case of this image, you almost certainly want to make it public. So in that case, the channel would be it's a public channel. And then within that, you'll have content that corresponds to the kind of quote unquote tokenized representation of this data. Again, maybe token is too strong of a word. So if you want to use any arbitrary embedding method, it can be put in here. But the important part is just that you've made a decision that, okay, it's in some message. It has the associated metadata that I need for my modeling task and for my ergonomics. And then in the content, that's where you keep however way you want to embed the data, that information goes there.
Thank you.
Okay.